Welcome to Louvain 1.2x. This course is a successor to Louvain 1.1x, the previous course. We assume as a prerequisite that you understand the concepts and also the notation of Louvain 1.1x, the Oz language, either by having followed Louvain 1.1x or by self-study. So Louvain 1.2x continues the story with three important topics. So first of all, data abstraction and state, and then concurrent programming, and finally, organizing all the concepts together in a coherent way in terms of programming paradigms. These are all essential concepts for programming in the real world. So the main theme of Louvain 1.2x is scaling up what we saw in Louvain 1.1x so it works in the real world. So the practical organization of Louvain 1.2x, so there are 7 lessons with homework exercises and a final exam. As before, the exercises will be done in the Mozart system and graded by our ingenious grader. So we will give a short introduction to these, but if you need a more full introduction, you have to go look at the introduction in Louvain 1.1x. So how is the course organized? So we have, first of all, in terms of certificate, there's either an honor code or a verified certificate. And then in terms of lessons, so there's 1 lesson per week, 6 lessons plus 1 bonus lesson, which I'll explain in a moment. The lessons start, as you know, November 17, and the end of the last lesson is January 12. So with the lessons come weekly exercises. These are worth 50% of the grade, the same as in Louvain 1.1x. There are conceptual exercises, multiple choice and fill in the blanks, and programming exercises using Mozart and Ingenious. So we give you 1 week deadline nominally, but in fact we add 2, so you have 3 weeks for each exercise. There are an infinite number of tries for each exercise, so you are not penalized for trying many times. The final exam, which is also worth 50% of the grade, starts on January 12. The final due date is 2 weeks later, not 3, January 26, and you get only 2 tries per exercise in the final, so be very careful to think before responding for the final. So let me explain a little bit the schedule. So the first 3 lessons are basically on data abstraction and explicit state. So we start by introducing the ideas, then an important paradigm that is based on them, object-oriented programming. And the way we explain object-oriented programming will maybe seem a little bit unconventional, but you'll see in a very nice way how all the different parts fit together. And then finally, we will apply this to the Java language. We'll extend it to multiple inheritance and add another concept called exceptions for handling abnormal situations. So that's the first 3 lessons. The next 3 lessons are on concurrent programming. So we start by introducing deterministic data flow, which is the simplest but still very powerful form of concurrent programming. And then techniques. How do you really program with this? How do you use higher order and so on? It's very interesting kinds of techniques that we will see. And then we have the bonus lesson on multi-agent data flow programming. In fact, originally we didn't think of including this lesson, but after talking with people, this lesson seemed so nice. I mean, the paradigm seemed so nice that we just couldn't leave it out. So we added it in because it's, in some sense, the most interesting all-around paradigm for concurrent programming. And then there's 1 week, a 1-week break for end-of-year festivities, 1 week that will not be counted at any of the deadlines. And the next lesson, number 7, starts on January 5. Here we take a step back and look at all the different paradigms and how it fits together. And also we will look forward, how you can continue on from here. And January 12 is the final exam, and January 26 is the end of the course. So the guest lecture, so the bonus lesson, lesson 6, is a lesson on multi-agent data flow programming. This lesson will be given by Saif Haridi. So this paradigm extends the deterministic data flow, which we will have seen just before, and you can add non-determinism exactly where you need it, but only there. So this makes it extremely powerful and yet also extremely flexible. So it is the best all-around paradigm for current programming that we know about. So this lesson will be given by Seif Haridi. So Seif Haridi, who's a close colleague of mine, he is professor at the Royal Institute of Technology in Stockholm, Sweden, and he's also chief scientist at a very interesting laboratory called the Swedish Institute of Computer Science. So the course textbook is the same as for Louvain 1.1x. It'll be Concepts, Techniques, and Models of Computer Programming by myself and Seif Haridi, published by MIT Press. So the same book for both courses. In fact, each course sees about 25% of the book. Both courses together, you will have seen about half of this book. So as for Louvain 1.1x, MIT Press makes available part of the book for the course, chapters 1 through 3. But in fact, this is not enough for the whole course. So we complement this by the slides. And I've also put in the course wiki a link to the last public draft of the book. So this public draft has all of the extra information that is not in the chapters 1 to 3. So with this, you have enough information to complement very nicely the lessons. Let me now talk about the content of Louvain 1.2x. So the overarching theme of Louvain 1.2x is how do we scale up the concepts of the simple paradigm functional programming. It's enough to write programs in any program you want, but it needs more to be able to realize programs that are in the real world. So there are several concepts that we will add. So abstraction is one of them. Data abstraction. This is an organizing principle, the main organizing principle that we will use to build very large software systems, large, complicated ones, millions of lines of code. And the real world is complicated, so programs have to be able to mirror this. We need programs that are larger than programs that could be written by one person. Teams of people have to be able to write them, and that's what we will use data abstraction for. The second concept, and an important concept next to data abstraction, is explicit state. And the reason why we need explicit state is to model change. Programs need to change. So a part of the program might need to be updated. The rest of the program stays the same. How do we do this? How do we model this? And this is important, of course, because the real world has change. So programs also have to be able to change. Parts of them change, parts of them don't. We have to be able to manage all of this. So explicit state is the concept we use for that. And then there is concurrency. So concurrency is a property of a system when you have many independent activities. Activities that are progressing independently that do not necessarily interact. So the real world, of course, is full of independent activities. We have to be able to mirror this structure inside of a program. And that's what concurrency is all about. But concurrency is actually quite complex to program in its most general form. So we introduce a simpler model called deterministic data flow. So this is a form of concurrency that always gives the same outputs for the same inputs. This is what we call determinism, and this allows us to simplify greatly how we program concurrent systems. So in Louvain 1.1x, we saw a first complete coherent paradigm called functional programming with its kernel language, with its techniques, higher order programming and so on, loops, invariance, recursion, and so on. Now we're going to build on that. We're going to see 4 more paradigms in Louvain 1.2x. These paradigms, each of them, will organize certain concepts into a coherent whole that we can then use to think about and build systems with. So in the first 3 lessons, we will see object-oriented programming. So this is a paradigm that is based on ideas from data abstraction. In lessons 4 and 5, we will see deterministic data flow. This is the simple form of concurrent programming that is so simple that we can program with the same good properties as functional programming. And then in lesson 6, we will extend this paradigm by adding what we call non-determinism where needed. So this turns it into a general concurrent programming paradigm. And because of the fact that most of your program can still be deterministic, can still use the simpler paradigm, and only a small part has to use the more complicated one, this is one of the reasons why this is the best all-around paradigm for concurrent programming that we know of. And then finally, in lesson 7, we will combine object-oriented programming ideas and multi-agent data flow ideas, because these two sets of ideas can be combined, and you can get the advantages of both in the paradigm called active objects. Now, let's start. So this first lesson, we'll talk about explicit state and data abstraction. So after this lesson, you will understand what it is that explicit state adds to functional programming. Functional programming is a general paradigm. You can program anything with it. It's what we call Turing complete. But something is added with explicit state. You will see exactly what it is in this lesson. You will also see how to build data abstractions. In fact, there are 4 fundamentally different complementary ways of building data abstractions for a given set of operations. You can package them and get 4 different ways of looking at it. Objects are only one of these 4 ways. So you will see all 4 ways, and you will see how some modern languages are actually taking advantage of more than one, but you will have the complete view of all 4. So this leads to the second paradigm, which in fact is based implicitly on data abstraction, and this is the paradigm of object-oriented programming.